Hello everyone, this is Monica Lupion and today's presentation is about unsteady state conduction. That is when there is a dependence with time. This is the general content of my presentation today. First of all, a brief introduction about the fundamentals of unsteady state conduction. And then we'll focus on the resolution of the general equation. As we saw in the case of steady state conduction, there are three different methodologies. One is the use of analytical tools to solve the equation of unsteady state conduction. Second is the use of graphical methods or graphical charts to relate the temperature and time. And finally, the numerical methods that we also mentioned in steady state conduction. Today's presentation will focus on the analytical solution, and the next presentation will be dealing with the graphical method. And finally, a summary. So what's unsteady state? It's the case that we have a dependence with time of the temperature. So the temperature not only depends on or changes due to the position, but in this case also due to time. In general, those systems or these systems, the steady state systems, are more difficult to solve than steady state because we don't only have to solve the dependence with position, but also with time. This is the general equation of heat conduction, as we know already. In previous classes, what we consider is that this term here, the dependence of temperature with time, was 0. Now we need to consider this term as well when we are solving the equation. As I mentioned a couple of minutes ago, there are three different methodologies. One is the analytical solution, and we know that there is a general case where we can use different mathematical tools, such as the separation of variables. Second, the graphical methodology. We'll see in the next presentation that there are some charts correlating the temperature and the time. And finally, the numerical method that we covered in previous classes basically is the use of some computing software such as MATLAB. So what's the general equation and how can we solve this general equation? The general equation, as I mentioned, we already know the general equation. Just to remind you that we can express this general equation in rectangular coordinates here, cylindrical coordinates, or spherical coordinates. Let's talk about the analytical method to solve this equation. So first, we need to know the general equation. We already know that, so no problem. And then the boundary conditions. Those two steps will be similar as in the case of the steady state conduction. What is new here in the case of unsteady state conduction is that in addition to the boundary conditions, we also need to consider the initial conditions. So the initial conditions must be satisfied. First of all, we need to solve or we need to know the function of the temperature in relation to the position and time. And once we know that, then we can apply the Fourier's second law in order to calculate the energy exchange. In the process of heating and cooling, the rate of energy transfer depends on the internal resistance and the surface resistance. we are going to see three different cases. First one, it's when the internal resistance is negligible. Second, when we don't consider any external resistance or is zero. And the third case will be the general case when both internal and surface resistances must be considered. As you can imagine, in general, these two cases here, either when we don't consider internal resistance or when we don't consider surface resistance, these two cases are in general much more simpler to solve than when we have to consider both internal and surface resistances. So let's begin with the systems with an negligible internal resistance. When there is no internal resistance within the body, within the medium, we can consider that the temperature inside remained essentially uniform at all times during the heat transfer process. So systems with no internal resistance satisfy the condition here that the temperature can be considered uniform with position and uniform at a given time. So there is no dependence on position, but mainly the time. The heat transfer analysis based on this ideal condition is usually called lumped system analysis. So the lumped systems are systems where we can consider that the temperature of the fluid, of the medium here, can be kept uniform. There is no dependence with the position. We can directly take the general equation, and since the temperature doesn't depend with the position, we can just do the integration over the time in this equation, in this general equation here. So basically what we are doing is transforming the partial differentiate equation into an ordinary differentiate equation. Once we do the integration and considering the initial conditions, it's very easy to solve. And this is the solution, the mathematical solution of this equation here when we have lumped systems. If we play around with this equation here of the temperature, and in particular, if we rearrange the terms in the exponent, as is indicated here, so basically what we do is to have two different factors here. So we rearrange the exponent. We can define this function, these variables here as the Biot modules, and this one related to the thermal diffusivity is defined as the Fourier modulus. Something very interesting about the Biot modulus is that if you take a closer look, this is the volume over the area, over the thermal conductivity, over the inverse of the convective heat transfer coefficient. So if you try to find if there is some physical meaning of this Biot modulus, and thinking about an analogy with the thermal resistance that we did in previous classes, we can say that this Biot modulus is equal to the internal resistance over the convective resistance. That is the internal resistance over the external resistance due to convection. So this group here will be the internal resistance, which depends on the thermoconductivity. And this value here is the resistance of heat transfer due to convection. In the case of lamped systems, when I mentioned the internal resistance has to be small in order to assume that there is an uniform temperature in the medium. In that case, the Biot modules need to be small. So the internal resistance is small as well. This equation here we can also draw just to solve numerically much more quicker, much more easier. So we can use this graph here that you can find in your textbook to solve the temperature and the heat transfer when we have a Biot module very small. And just a criteria that we apply is that the Biot number is below 0.1. We will assume that there is no internal resistance, and therefore we can directly apply this equation here, or equivalent, or which is equivalent to this graph here. This graph is just the graphical representation of this equation. So in the x axis we have the Biot modules and the Fourier modules, and in the y axis there is the temperature at a given time minus the temperature in infinity over the initial temperature minus the temperature infinity. This is an example that I would like you to try. I will finish first the presentation, and then we can spend some time solving this example here. But I would like you to stop the video for a while and try to solve it, and then we can cover the next section. Okay, so I mentioned that we're going to consider two different conditions. One is systems with negligible internal resistance, and the second case is when there is no surface or external resistance. If you remember from a few minutes ago, we defined the Biot modules as the relationship between the internal resistance, which is this value here, the volume over the area over the thermal conductivity, over the convection resistance. Now we have just the opposite case as in the previous one. So instead of having a very small internal resistance, what we want to have now is a very small surface resistance. That means that the Biot number has to be large. If we consider that there is no resistance over the surface, the ideal case, then we can assume that the temperature of the surface, Ts, is equal to T infinity, and that's a constant over the time. So when it comes to solve the equation, it's much more easier because we can simplify having the temperature constant with time. We can only need to worry about the position. This is an example of solution once we apply the analytical methodology in a flat slab. You can have, or you can take a look to the details in your textbook. But normally, as you can see here, the equations get more and more complicated. This example was just a very simple geometry. So if we have more complex geometries, it's almost impossible to apply analytical method. In those cases, what we do is to apply some charts that will help us to solve the equation. This is a graph from your textbook, and it's in chapter 18, but you can also find this one and much more in the appendix F. In this case, what we can see is that there is different lines that correlate the temperature factor here with the thema diffusivity and time and deposition. The assumptions that we need to take in order to use this graph is that the solid or the medium has to have an initial uniform temperature T sub 0 and a constant surface temperature T sub S. So it's exactly what we just defined here with when we have systems with no surface resistance. This is another example on how we can determine the temperature with the time. So I would like as well to take you a few minutes and try to solve it before we move to the next piece of presentation.